We were talking about heat and work, and we talked about pressure volume work, where you have a gas expanding its volume against an external pressure, and that's the sort of work we're going to be looking at. That's this down here. And we've talked about heat, which is Q, and that's mc delta T. And these are the two ways that energy can be exchanged between the system and the surroundings. So the change in internal energy in a chemical reaction is a measure of all the energy, both heat and work, that get exchanged between the system and the surroundings. And so we could determine delta E by measuring Q and W. So the change in E is going to equal Q plus W. What if there's no change in volume? W is equal to negative P delta V. What if delta V is 0? Then the work is 0, right? So if there's no change in volume, then W is equal to 0, and so at constant volume, the change in internal energy for the reaction is equal to the heat exchanged. And there's a V there because that's specifying at constant volume. So it isn't practical to look at temperature changes of individual species in a reaction. So we monitor it using the surroundings. So a bomb calorimeter is used. And this is a little bit like that beaker of water that we put the hot piece of metal into and we measured the temperature change in the metal. So here, Q for the system is equal to negative Q for the surroundings, and the surroundings is the calorimeter. So Q system is equal to negative Q of the calorimeter. The heat lost by the system is gained by the calorimeter. So in general, calorimetry, measuring calories, is just a way of measuring the heat of reaction by observing temperature changes in the surroundings. So we've got the system, which is going to be our chemical reaction, and then we're going to observe temperature changes in the surroundings. We keep it at constant volume, and so then we're only looking at heat, and we don't have to deal with work. So this is an illustration of a bomb calorimeter. Oops, wrong button. So this is the bomb part. Nothing explodes, though. They use these to determine the calorie content of foods. So you could do this like with a single peanut. You could put a peanut in there and burn it and see how much energy is released, how much heat is given off. So this little bomb in here contains oxygen, a platform for the sample to sit on, and then it's got ignition wires so that you can pass electric current through here and get the thing to start burning. Outside the little bomb is water and an insulated container, and we've got a thermometer so we can measure the temperature, and we've got stirring so that the heat gets uniformly spread around. So the calorimeter constant is the heat capacity of the calorimeter. This is not the specific heat capacity. Here, heat capacity is useful. Specific heat capacity works for any mass, but since you're using the same calorimeter over and over and over again, its mass is always going to be the same. And so what we mean here by C sub cal is the mass of the calorimeter times the specific heat capacity of the calorimeter. And because neither of those is changing, we just lump them together. So if no heat escapes, then the heat gained by the calorimeter will equal the heat lost by the reaction. So Q for the calorimeter is the heat capacity times the change in temperature. That's equal to, but opposite in sign, to Q for the reaction, which is equal to the change in energy for the reaction. So let's do an example. When 1.55 grams of liquid hexane undergoes combustion in a bomb calorimeter, the temperature rises from 25.87 degrees Celsius to 38.13 degrees Celsius. Find delta E reaction for the reaction in kilojoules per mole of hexane. The heat capacity of the bomb calorimeter, which was determined in a separate experiment, is 5.73 kilojoules per degree Celsius. Okay, we read the problem. Now we find the numbers. And identify what we're trying to find. Delta E in kilojoules per mole hexane. So I'm going to write these numbers down. So we've got 1.550 grams of hexane, C6H14. We have 25.87 degrees. That's not an 8. That doesn't look like an 8 either. 87 degrees Celsius. And we have 38.13 degrees Celsius. And we have a very tiny eraser. And then we have 5.73. And that is kilojoules per degree Celsius. Let's start at the end. So this is the heat capacity for the calorimeter, and so that's called C-cal, the heat capacity of the calorimeter. And then these are temperatures, right? Which one's the initial temperature? 25. Right? That's where it starts. So that's the initial temperature, and this must be the final temperature. And then this is a mass, but that's not the mass of substance that we're multiplying by a specific heat. That's just a mass. It's the mass of hexane. So by looking at these two guys, we can find that delta T is equal to 38.13 minus 25.87, or 12.26 degrees Celsius. So the heat absorbed by the calorimeter is equal to the heat capacity of the calorimeter times the change in temperature. So we have both of those numbers now. So we've got 5.73 kilojoules per degree Celsius times 12.26 degrees Celsius. So we multiply those, and we get Q-cal is equal to 70.2498. It would only have 3 sig figs. The degrees Celsius cancel out, and I'm left with a unit of kilojoules. So that's Q for the calorimeter. What's the relationship between Q for the calorimeter and Q for the reaction? The heat lost by the reaction is absorbed by the calorimeter. So their values, their magnitudes are the same, but they are opposite in sign. So to find Q for the reaction, we're just going to take this and multiply by -1. So Q reaction equals negative 70.2498 kilojoules. And Q reaction is equal to the change in energy for the reaction. The only thing we're missing here is that it wants us to specify kilojoules per mole of hexane. We have kilojoules we got this from 1.55 grams of hexane. So we could say that's kilojoules per 1.550 grams of hexane. Yeah, 14. Well, could we convert that into moles? Sure we could. So 1.550 grams of C6H14. We're going to multiply by moles and divide by grams. We have 6 times 12.01 plus 14 times 1.008. 86.172 grams for every mole of hexane. So 1.55 divided by 86.172 gives us 0.0179, let's see, 873 moles. Okay? So instead of the mass, I'm going to write the moles in there. So I'm going to get rid of that because I want it per mole. So now I've got negative 70.2498 divided by 0.0179873 equals. This is negative 3905.5 3 sig figs kilojoules per mole. So if we round that, the best way to round that is to say this is negative 3.91 times 10 to the third kilojoules per mole. Kind of squished down there in the corner. Is this 3,905, is that a big number or a tiny little number? 3,000?
Oh, no. Sorry. I thought 3.91. Okay.
3.91 is pretty small, but 3,905 is a big number.
Yeah.
How do I feel about big paychecks? Positive,
Yeah.
right? So this is a positive exponent. Some of you are doing all the work correctly on the worksheet, and then you're converting your answer to scientific notation and the sign is wrong. So watch out for that. Any questions?